On a cold March night in 1999, a sudden, violent flash ripped through the pitch-black sky over Serbia. The target was a billion-dollar ghost. The F-117 Nighthawk was engineered to be entirely invisible to enemy radar. An aging Soviet-era missile system achieved the interception. It relied on analog tracking and physical patience to find the high-tech aircraft. For over a decade, both military commanders and the public believed the F-117 was untouchable. It was the gold standard of modern warfare. But invisibility in aviation is a physical state, heavily dependent on highly fragile conditions. It breaks the moment those conditions change. To understand how the Nighthawk fell, we have to look past the myth of an invisible plane and trace a fatal chain of microscopic and mechanical engineering flaws. The aircraft's jagged shape gets most of the attention, but its first line of defense was its skin. A thick matte black coating covered the exterior, designed specifically to swallow incoming radar waves. That coating was highly susceptible to environmental stress. The friction of flight, intense heat, and simple rain aggressively wore down the material. Ground crews spent grueling hours meticulously patching and repainting peeling edges by hand, fighting thousands of microscopic cracks. In stealth engineering, surface consistency is everything. Even a millimeter-wide peeling edge in the paint creates a jagged barrier. When a radar pulse hits that tiny irregularity, it violently deflects backward, creating a bright reflection. An aircraft relying on a hand-painted, heavily applied coating is inherently unreliable. The first fatal flaw was a failure in materials. Down on the ground, Serbian Colonel Zoltan Dani was actively hunting the aircraft using outdated Soviet-era defense systems. He lacked modern targeting computers. His crews relied on worn paper maps, manual tracking, and immense patience. Crucially, they used long-wave radar. Tight, high-frequency waves from modern systems hit the sharp angles of the F-117 and deflect away. But wide, low-frequency waves behave differently. They wrap around the aircraft, catching on those microscopic paint gaps and worn edges. This bounced a faint signal back to the source. Operators stared at heavy static on old CRT monitors, searching for tiny, flickering anomalies. Technological obsolescence gave the Serbian crew the exact tool required to exploit the aging, physical skin of the aircraft. Even with peeling paint and long radar waves, the returning signal was too weak for a fatal weapons lock. The aircraft was mostly hidden. Then came the unavoidable operational requirement. To drop its payload, the Nighthawk had to split apart its smooth belly and open its bomb bay doors. In an instant, the highly calculated radar-deflecting geometry of the aircraft was compromised. Deep, jagged internal machinery faced the sky. That exposed interior acted as a massive radar reflector, and the aircraft glowed on the monitors below. For exactly 3 seconds, the target was visible. Danny's crew secured a hard lock, and 2 missiles climbed into the night. The event highlighted a persistent mechanical trade-off. Stealth relies on a perfect geometric profile, but combat aircraft must break their own silhouette to complete the mission. The wreckage in that muddied Serbian field showed the limits of masking an aircraft with external paint. The debris proved that a surface-level solution was too fragile for a modern battlefield. A billion-dollar project was brought down by peeling edges and open doors. Stealth could no longer be treated as an external layer. Engineers were forced to rethink how an airframe was constructed from the inside out. In newer fighters, stealth is woven directly into the composite structure of the aircraft itself. It relies on advanced materials built into the panels rather than masking paint applied over them. The Nighthawk's failure forced a shift toward aircraft built from the ground up with stealth integrated into the very carbon fiber of the frame.